universe is changing. Dark energy, cosmic expansion, and the fate of everything. Welcome back to Asleep in Class, where we turn quiet lectures into restful journeys through history, science, invention, and the wider world. Here, curiosity can slow down, the day can loosen its grip, and there's no test waiting at the end. And if there is a sleepy lesson you would like covered in class next, please feel free to leave it in the comments below. Tonight, the classroom opens into the deep universe, where distant galaxies carry old light. Space itself stretches between them, and the future once seemed almost settled. For generations, astronomers measured that future through distance, brightness, motion, and time. They built a powerful story of expansion, acceleration, darkness, and cosmic fate. Yet the newest maps of the sky have begun to press gently against one of that story's deepest assumptions, leaving the ending less certain than it once appeared. The universe before it moved. For most of human history, the universe did not appear to move in any large, obvious way. The sun crossed the sky, the moon changed shape, and the planets wandered against the background stars along paths that looked strange beside the steadier constellations. Comets arrived without warning. Eclipses briefly turned daylight into something unnatural. Yet, behind those motions, the larger heavens seemed firm. Stars returned to familiar places, and seasons came back in recognizable order. The sky did not look like an object with a beginning, a changing structure, or a distant future. It looked like a permanent arrangement, marked by rhythm. That impression did not come from carelessness. Ancient and early modern observers watched the sky with patience and practical purpose, using the motions human eyes could follow to build calendars, guide ships, plant fields, and mark sacred days. Those motions were real, but they stayed local and repeating. The visible sky offered cycles more than history. Nothing in ordinary observation showed space stretching, or distant galaxies carrying evidence of a younger universe. A stable cosmos was a reasonable answer to the evidence then available. In 1687, Isaac Newton published the Principia, one of the central works in the history of physics. The book gave gravity and motion a mathematical language strong enough to connect Earth and sky inside one system. Newton showed that falling bodies, orbiting moons, and planets moving around the sun followed laws rather than separate kinds of behavior. A stone dropped near the ground, and the moon circling Earth belonged to the same physical order. Newtonian physics gave the cosmos a deep mechanical confidence. In that framework, space and time worked like a vast fixed stage. Objects moved across it, forces changed their motion, and the stage itself was not yet understood as something that might bend, stretch, or carry its own large-scale history. Gravity reached across distance. Planets followed calculable paths. As astronomers predicted eclipses and planetary positions with increasing precision, the frame of reality looked steady enough to calculate, even while the universe still held many unknowns. That confidence shifted in the early 20th century when Albert Einstein published the general theory of relativity in 1915. The theory did not merely improve Newton's mathematics, it changed the meaning of gravity. In general relativity, gravity is not simply a force pulling objects through fixed space. Matter and energy shape spacetime, and objects move along paths created by that curvature. A planet follows the curve made by the sun's mass, not because space sits silently underneath the motion, but because space and time themselves participate in the structure. From that idea came a larger possibility. If spacetime curved near a star, then the universe as a whole might also have a shape and behavior. Space could no longer be treated only as an empty container where cosmic events happened. It could respond to matter, be described by equations, and at least in principle, expand, contract, or take on a large-scale geometry. A theory designed to explain gravity also made the universe itself into a physical subject. Einstein saw that implication quickly. In 1917, he applied general relativity to cosmology, the study of the universe as a whole. A static universe still felt natural to many scientists at the time. The Milky Way's true place had not yet been settled, and the spiral nebulae seen through telescopes had not yet been firmly recognized as galaxies beyond it. Without reliable distances to those faint spirals, the universe could still be understood as a vast, but mostly fixed stellar system. Einstein's equations resisted that stillness. Gravity pulls matter together, so a universe filled with matter should not remain perfectly balanced without some opposing effect. If nothing countered gravity at the largest scales, a static universe would tend toward collapse. To make the model stand still, Einstein introduced the cosmological constant, usually represented by the Greek letter lambda. In that early model, lambda acted as an added term in the equations, a mathematical pressure that could balance gravity and hold the universe in place. Other relativistic models showed how unstable the old stillness had become. Willem de Sitter, a Dutch mathematician and astronomer, developed cosmic models that used Einstein's new theory in different ways, pointing toward stranger possibilities than a simple fixed universe. Theory alone could not settle the question, though. Cosmology still needed an observational anchor, reliable distances to the spiral nebulae, and a clear pattern in their light. The cosmological constant did not begin as a telescope discovery or a directly observed substance. It began as a way to make a powerful new theory match the static universe that still seemed plausible. Later retellings sometimes reduce it to a simple mistake, but Einstein worked before the decisive galaxy distance and redshift evidence arrived. Lambda began as a stabilizer. It would later return with a different meaning, attached not to stillness, but to acceleration. While theorists tested the mathematics of spacetime, astronomers faced a more basic question: how large was the universe? In 1920, Harlow Shapley and Heber Curtis took opposing positions in what became known as the Great Debate. Shapley argued that the Milky Way was extremely large and that the spiral nebulae belonged inside it. Curtis argued that those spirals were separate island universes, immense star systems outside the Milky Way. Each answer gave physics a different cosmos to explain. If Shapley was right about the spiral nebulae, then the Milky Way held the main contents of the universe, even if it was larger than earlier astronomers had thought. If Curtis was right, then the Milky Way was only one galaxy among many, and the scale of reality expanded far beyond the older stellar frame. Their argument was not only about distance, it was about whether the universe was a single great system or a population of systems spread through deeper space. The still cosmos could survive only while distance remained uncertain. Newton had given motion a mathematical order. Einstein had made gravity deeper and more flexible, and de Sitter had shown that relativity allowed stranger models. But the old frame did not truly break until astronomers found better ways to measure the spiral nebulae. If you are enjoying this quiet lesson on deep space, time, and the structure of the universe, please subscribe for more calm journeys through history and science. The next turn came from stars, whose brightness rose and fell in measurable rhythms, from faint galaxies placed far beyond the Milky Way, and from light stretched toward red as space carried it across the dark. Galaxies begin to flee. The first break came through a simple question: how far away are the spiral nebulae? Through early telescopes, they looked like pale coils of light suspended among the stars. Some astronomers treated them as small clouds inside the Milky Way, while others suspected they were immense star systems far beyond it. Appearance alone could not settle the matter. A small nearby object and a huge distant object can look similar from Earth. To change the scale of the universe, astronomers needed a reliable way to turn light into distance. That tool came from Henrietta Swan Leavitt at Harvard College Observatory. Working with photographic records of stars that changed brightness over time, she studied Cepheid variables, stars whose light rises and falls in a regular rhythm. By comparing many Cepheids, Leavitt found that the length of a star's cycle was tied to its true brightness. A slow-pulsing Cepheid was intrinsically brighter than one with a shorter cycle. This became the period luminosity relationship. The period was the timing of the star's pulse, while luminosity meant how bright the star truly was, not merely how bright it looked from Earth. That distinction mattered because apparent brightness changes with distance. A lamp across a room can look dimmer than a candle nearby, even if the lamp is truly stronger. Stars create the same problem on a much greater scale. When an astronomer knows a Cepheid's true brightness from its pulse rate and compares it with how faint the star appears, the difference becomes a distance clue. Leavitt's Cepheids gave astronomy a measuring tool that reached farther than ordinary parallax, the small apparent shift of nearby stars against the background sky as Earth moves around the sun. Edwin Hubble used that tool at Mount Wilson Observatory, where the large Hooker telescope gathered enough light to study faint stars inside spiral nebulae. In the 1920s, he identified Cepheid variables in the Andromeda Nebula. Their periods revealed their true brightness. Their faint appearance then showed that Andromeda was far too distant to sit inside the Milky Way. Publicly announced in the middle of the decade, the result made Andromeda not a nearby cloud, but a separate galaxy, an island of stars beyond our own. The Milky Way was no longer the great container of nearly everything visible. It became one galaxy among many, part of a far larger cosmic population. The debate between Shapley and Curtis did not end by argument alone. It ended because a pulsing star gave distance a number, and that number pushed the spiral nebulae beyond the old boundaries. Once distance opened the universe outward, another clue gained new meaning. Vesto Slipher, working at Lowell Observatory, had measured the spectra of spiral nebulae before Hubble's distance results became decisive. A spectrum spreads light into its component colors, like a scientific version of a rainbow. And within that spread, astronomers can see lines made by atoms. Those lines have expected positions. When they shift, the change can reveal motion along the line of sight. Many of Slipher's spiral nebulae showed redshift, meaning their light had been stretched toward longer, redder wavelengths. In ordinary motion, this can happen when a source moves away from the observer, much as a sound changes pitch when its source moves past. Slipher's measurements showed many spiral nebulae receding at remarkable speeds. At first, those speeds were puzzling because distances remained uncertain. Once the nebulae became galaxies beyond the Milky Way, their redshifts were no longer just strange motions. They became part of a larger cosmic pattern. Hubble brought distance and redshift together with important observational help from Milton Humason, who measured faint galaxy spectra at Mount Wilson. In 1929, Hubble published the distance-redshift relation. The farther a galaxy appeared to be, the faster it seemed to recede. This relationship is often called Hubble's law. Later, it became known more formally as the Hubble-Lemaître law, because Georges Lemaître had already described an expanding universe in relativistic terms. Distance measurements, spectral shifts, and relativity were beginning to point in the same direction. Nearby galaxies could have their own local movements, but across greater distances, the relation became clear enough to change cosmology. Instead of galaxies merely moving through fixed space, space itself appeared to be stretching on the largest scales. As the universe expanded, the distance between widely separated galaxies increased. That did not place Earth at the center, while galaxies flew away through an empty background. Observers in another distant galaxy would see a similar pattern. The relationship came from space stretching between galaxies, not from a special position held by the Milky Way. The old static picture could no longer carry the evidence. Leavitt's Cepheids made deep distance measurable. Andromeda and other spirals moved beyond the Milky Way. Slipher's redshifts showed many of those distant systems receding. Humason extended the faint galaxy measurements, while Lemaître's relativistic expansion gained a stronger observational foothold. The sky that once looked permanent had gained a history written into faint light. If galaxies were receding now, then the next question reached backward. What kind of universe appears when that expansion is traced toward an earlier, denser past? The fire behind the darkness. If galaxies were receding from one another, then expansion had become more than motion. Astronomers could follow it outward into the future, but they could also trace it backward, toward an earlier state when the distances between galaxies were smaller. Scientists were no longer asking only whether the universe stood still. They were asking what kind of cosmos must have existed before the galaxies spread so far apart. Georges Lemaitre had already taken that step before the expanding universe became widely accepted. A Belgian priest and physicist, he worked seriously inside modern relativistic cosmology. In 1927, he described an expanding universe within the framework of general relativity. If space was expanding now, then the past pointed toward a denser state. In 1931, he pushed the idea further with what he called the primeval atom. He was not describing an ordinary atom as modern chemistry understands it, but reaching for a way to describe an extremely compact beginning. The phrase can sound strange now, but the central movement was important. Lemaitre was not picturing an ordinary explosion in empty space, where matter bursts outward from one location into a pre-existing void. The expansion belonged to space itself. Traced backward, that movement suggested that the whole observable universe had once been hotter, denser, and closer together. The past was becoming physical, not merely philosophical. That backward path opened a new kind of cosmology. A hot, dense beginning would not only have a history, it would have consequences. Early matter should have behaved according to nuclear physics. Light should have interacted with charged particles. If those changes left evidence behind, then the early universe could be tested, not just described. In the mid-20th century, George Gamow helped turn that possibility into a physical model. Ralph Alpher and Robert Herman worked with him on what a hot early universe would do as it expanded. The young cosmos would have been dense enough for nuclear reactions, allowing some of the simplest atomic nuclei to form. This process became known as hot Big Bang nucleosynthesis, meaning the early formation of simple nuclei in the first hot stages of the universe. It helped explain why the universe is made mostly of hydrogen and helium. Smaller amounts of heavier elements were made later inside stars and stellar explosions. This was different from the galaxy distances and redshifts that had broken the static universe. It reached into composition. If the universe had once been hot enough for nuclear reactions everywhere, then the abundance of light elements should carry a memory of that early fire. Hydrogen and helium were not just substances floating through space. They became part of the universe's oldest chemical testimony. Gamow, Alpher, and Herman also pointed toward another leftover. In the early universe, matter was not arranged as quiet atoms. Instead, it formed a hot plasma, a dense mixture of charged particles and radiation. Since electrons were not yet settled into atoms with nuclei, light could not travel freely for long distances. It scattered again and again through the charged material, like a signal trapped in a bright fog. The universe was full of light, but not yet transparent to it. As space expanded, it cooled until conditions allowed electrons and nuclei to join into neutral atoms. After that transition, light no longer scattered constantly from free charged particles and could travel across space. The released light did not disappear. Space stretched it into cooler, longer wavelengths until it settled into microwaves. This leftover glow is now called the cosmic microwave background. It can be thought of as fossil light, not because it is solid or buried, but because it is surviving evidence from an earlier state of the universe. In 1965, Arno Penzias and Robert Wilson, working at Bell Labs, found a persistent microwave signal with the Hubble horn antenna. They were not searching for the early universe at first, but trying to understand unwanted noise in a sensitive radio instrument. The signal remained after ordinary explanations were removed. At nearly the same time, a Princeton group, including Robert Dick, James Peebles, Peter Roll, and David Wilkinson, was preparing to look for the same kind of relic radiation. That timing mattered because the Bell Labs signal matched what cosmologists already expected from a hot, early universe. The discovery became one of the strongest pieces of evidence for the Big Bang model, and Penzias and Wilson later received the 1978 Nobel Prize in Physics for their work. The cosmic microwave background was not a picture of the beginning itself. It was a relic from the time when the universe changed from opaque plasma to transparent space. Later missions made that relic far more precise. COBE measured the background and showed how closely it matched the expected thermal pattern. WMAP mapped its tiny variations in greater detail. Planck refined the measurements further, giving cosmologists a clearer picture of the early universe's temperature pattern, composition, and age. Those tiny variations mattered because they were small differences in density that later helped matter gather into galaxies and clusters. By this point, the universe had become a historical object. It had a hot beginning, a cooling history, a transition into transparent space, a background glow, and measured structure in that glow. Its age could be estimated at about 13.8 billion years. The sky no longer offered only motion away from us. It carried evidence of an earlier cosmos still visible in microwave light. Expansion first gave the universe motion. The background glow gave that motion a measurable past. Galaxies receding from one another were no longer only markers of present movement, but signs of a cosmic story that could be followed backward into heat, density, atoms, and leftover light. Once that past became measurable, the next question changed again. Had expansion always unfolded at the same pace, or had the universe's outward motion shifted across time? The expansion speeds up. Once the universe had a measurable past, expansion became more than a discovery of motion. It became a history that could be compared across time. Galaxies showed that space was stretching. The cosmic microwave background showed an earlier cosmos that had once been hotter, denser, and younger. Now the question was no longer whether the universe had changed, but how its expansion had changed between that early state and the present sky. For much of the 20th century, the natural expectation was that gravity should act as a brake. Matter attracts matter, so galaxies, gas, stars, and unseen mass should pull on one another across space. Even while space widened, that pull should slow the outward motion over time. A universe with enough matter might eventually halt and collapse. A universe with less matter might continue outward forever, though more and more slowly. To test that expectation, scientists needed distance markers that could reach far across cosmic time. Nearby galaxies could show the present pattern, but distant galaxies show older light. Looking deep into space also means looking backward, because light needs time to travel. If astronomers could measure both distance and redshift for objects at great range, they could compare distance with how much space had stretched since the light began traveling. Type Ia supernovae became one of the key tools for that work. A supernova is an exploding star, but type Ia supernovae are especially useful because their brightness behavior can be calibrated. They are often called standardizable candles. That does not mean everyone is perfectly identical. It means their light curves allow astronomers to correct for differences and estimate true brightness. Once true brightness is compared with apparent brightness, distance can be estimated. This made type Ia supernovae powerful markers across deep space. Their redshifts showed how much the light had been stretched, while their apparent faintness helped show how far away they were. Together, those measurements let cosmologists place a supernova within cosmic history and test how expansion had shifted while its light crossed space. The method was difficult because distant supernovae are faint, brief, and scattered across enormous volumes of sky. By the late 20th century, improved telescopes, detectors, and search methods made large observing campaigns possible. Two major teams pursued the answer. One was the Supernova Cosmology Project, led by Saul Perlmutter. The other was the High-Z Supernova Search Team, associated with Brian Schmidt and Adam Rees. Both groups were trying to determine how much expansion had slowed. Their expectation was reasonable. Gravity should have pulled against expansion, and the data were supposed to reveal that deceleration. The result, announced in 1998, was surprising. The distant type Ia supernovae appeared dimmer than expected in a universe whose expansion was slowing under gravity alone. That faintness meant they were farther away than the simplest slowing expansion models predicted for their redshifts. The best interpretation was not that expansion had slowed less than expected. It was that expansion had begun speeding up. The universe was not merely expanding. Its expansion was accelerating. That result changed cosmic fate. Gravity alone should have slowed the expansion, even if it could not stop it. Instead, something appeared to be pushing the large scale stretching in the opposite direction. Scientists gave that unknown cause the name dark energy. The name did not identify what it was, and it did not mean the effect had been directly seen as a substance. It marked an invisible influence inferred from cosmic expansion. Dark energy should not be confused with dark matter. Dark matter is inferred from gravitational effects on galaxies, galaxy clusters, gravitational lensing, and large-scale structure. It behaves like matter because it clumps and pulls gravitationally, even though it does not shine. Dark energy is different. It is inferred from the accelerated expansion of space itself. Instead of helping matter gather, it is associated with expansion speeding up. The discovery also brought back Einstein's old cosmological constant in a new role. In 1917, Lambda had helped Einstein build a static universe. After expansion was accepted, that original purpose no longer held. Yet the same term could also act like a constant energy of empty space. Matter thins out as space grows, while this kind of effect would not thin away in the same way. In that newer interpretation, the cosmological constant became one possible explanation for dark energy. The mystery became sharper because empty space, which sounds like nothing, might have a measurable effect on the largest scale. This return did not mean scientists suddenly understood the cause. It meant the equations had a place where the observed acceleration could fit. A simple constant dark energy could be added to the developing standard model, then tested against supernovae, the cosmic microwave background, and galaxy surveys. The result was powerful, but it also carried a deep unease. The dominant influence on cosmic expansion had been named through its effect, not directly identified. In 2011, the Nobel Prize in Physics was awarded to Saul Perlmutter, Brian Schmidt, and Adam Rees for the discovery of the accelerating expansion of the universe through observations of distant supernovae. The prize marked how large the change had become. The late 20th century question had begun as an attempt to measure cosmic slowing. It ended by revealing a universe whose expansion was speeding up. If acceleration continued in the simplest way, distant galaxies would grow more isolated from one another over immense stretches of time. The universe would become colder, emptier, and harder to connect across its widening distances. Gravity would still bind galaxies, stars, planets, and local systems, while the largest separations kept stretching. Cosmic fate had become tied to an unknown component. The still universe had already fallen. The merely expanding universe had changed as well. Expansion was no longer only a motion traced backward into heat and light. It had become a shifting behavior, shaped by something dark, persistent, and not yet understood. The discovery gave cosmology a new standard story, but that story rested on a strange central component. To understand that modern model, the next step is to look at its dark side, the matter that does not shine, the energy that drives expansion, and the framework that holds them together. The dark side of the standard model. The modern framework begins with an unsettling balance. The universe can be measured with remarkable precision, yet most of what shapes it is not directly visible. It began hot and dense, expanded, cooled, formed galaxies and clusters, and later accelerated. These ideas became part of a wider framework linking the cosmic microwave background, galaxy surveys, supernova distances, gravitational lensing, and the large-scale pattern of matter. That framework is often called lambda cold dark matter, or Lambda CDM. Lambda represents the cosmological constant, the term associated with dark energy in the simplest version. Cold dark matter refers to matter that does not shine and moves slowly compared with light. That slower motion allows unseen mass to collect into cosmic structures over time. The universe is shaped mostly by two dark components, one that helps matter collect, and one that affects the expansion of space. Ordinary matter is only a small part of that picture. It means atoms and the things made from atoms, including stars, gas, planets, dust, oceans, rocks, and living bodies. It reflects light, absorbs light, emits light, forms chemistry, and builds the visible world. Yet in the Standard Model, familiar material makes up only about 5% of the total cosmic budget. Ordinary matter is everything familiar, but familiarity is not the same as dominance. Dark matter makes up a much larger share, about 27% in common Planck-era estimates. It does not shine, but gravity reveals its presence. Galaxies rotate in ways that visible stars and gas alone cannot explain. Galaxy clusters hold together and bend light more strongly than their visible contents would allow. Gravitational lensing shows extra mass by revealing how mass curves the path of light from more distant objects. Across large scales, this unseen component also helps explain how galaxies and clusters formed from the tiny early density differences seen in the cosmic microwave background. The word cold matters because dark matter moves slowly enough compared with light to settle into gravitational patterns. If the unseen material moved too quickly in the early universe, it would smooth out small clumps before galaxies could form. Cold dark matter gives structure time to grow and provides an invisible gravitational framework where ordinary matter can collect, cool, and form stars. Dark energy makes up the largest share, about 68% in common estimates. Its role differs from dark matter's role. Dark matter pulls and clumps, while dark energy is tied to the expansion history of the universe, especially the observed acceleration. In the simplest Lambda CDM version, dark energy behaves like a constant property of space. It does not gather into galaxies the way matter does. Instead, it remains associated with the large-scale behavior of space itself. Those percentages are approximate and model-dependent. They are not separate piles of material that have been directly scooped up and weighed. They come from fitting many observations at once. The cosmic microwave background gives an early universe reference point and helps anchor the age of the universe at about 13.8 billion years. Supernovae show distance and redshift behavior across cosmic time. Galaxy surveys show where matter has gathered. Gravitational lensing shows how mass bends light. Together, those measurements allow Lambda CDM to give a successful account of the broad cosmic pattern. One of the most important tools in that pattern is baryon acoustic oscillations, often shortened to BAO. The phrase points back to the young universe. Before atoms formed, ordinary matter and radiation were coupled in a hot plasma. Pressure waves passed through that early material, somewhat like sound waves moving through a medium. When the universe cooled enough for atoms to form and light to travel freely, those wave patterns left a preferred scale in the later distribution of matter. That preferred scale became a cosmic ruler. In galaxy surveys, astronomers can look for the regular statistical spacing left by those early waves. The ruler is not a line drawn between two obvious galaxies. It is a pattern that appears when millions of galaxy positions are studied together. Because the scale is connected to early universe physics, it can be used to measure cosmic distances and track expansion across different eras. This is why the Standard Model earned respect. It did not merely name unknowns. It made predictions and survived comparison with many measurements. It linked the early glow of the cosmic microwave background with the later arrangement of galaxies. It tied supernova distances to expansion history. It connected invisible mass with galaxy rotation, cluster behavior, gravitational lensing, and the growth of large-scale structure. A framework that can hold those pieces together is not weak simply because some components are mysterious. But the mystery is real. Dark matter remains unidentified. Scientists can measure its gravitational effects, but no confirmed particle or substance has been directly established as the dark matter itself. Dark energy is even stranger. It is inferred from accelerated expansion and modeled through Lambda in the simplest version, but its physical nature remains unknown. The names are not explanations, but disciplined placeholders attached to measured effects. Unknown does not mean invented. It means the evidence points to something whose deeper nature has not yet been found. That tension sits at the heart of modern cosmology. The Standard Model is successful enough that it cannot be casually dismissed, but incomplete enough that it cannot be treated as final. It gives the universe a coherent history from early plasma to galaxies, clusters, acceleration, and present structure. Most of what governs that history remains dark, because the measurements point to influences that ordinary light does not reveal. The next step is not to throw the model away. Precision invites pressure. If Lambda CDM is right in its simplest form, then dark energy should behave like a constant part of space across cosmic time. If better maps can measure expansion history more finely, they can test whether that assumption holds. The question becomes quieter and sharper, not whether the Standard Model has failed, but whether the newest maps reveal where it bends. The new map at the edge of certainty. Dark energy became one of the deepest tests of the modern cosmic story. If the simplest version of Lambda CDM is correct, then dark energy behaves like a constant property of space. Its influence may become more important as matter thins across cosmic time, but the dark energy itself does not change its basic behavior. That assumption gives the Standard Model much of its clean mathematical strength. It also gives astronomers something precise to examine. The work requires more than a few bright objects. It requires a survey large enough to compare different eras of cosmic history. Supernovae can show distance and redshift across time, while galaxy surveys add the wider pattern of matter itself. If enough galaxies and quasars are recorded, their positions can reveal how the universe expanded while light crossed billions of years of space. One of the most important instruments built for that work is the Dark Energy Spectroscopic Instrument, usually shortened in speech to DESI. It is installed on the Nicholas U. Mayall 4-meter telescope at Kitt Peak National Observatory in Arizona. Rather than collecting pictures in the ordinary sense, DESI gathers optical spectra from enormous numbers of galaxies and quasars. A spectrum breaks light into measured wavelengths, which allow astronomers to estimate redshift and place distant objects within a three-dimensional cosmic map. Redshift matters because it is not only a sign that light has stretched, it is also a depth marker. Light from nearby galaxies shows the more recent universe, while light from distant galaxies and quasars shows earlier times because it has traveled for billions of years before reaching Earth. With many redshifts taken across many directions, astronomers can arrange cosmic objects by sky position and look-back time. DESI also uses baryon acoustic oscillations, the ancient pattern introduced by pressure waves in the early universe. Those waves left a preferred spacing in the later distribution of matter. When millions of galaxies are mapped, that spacing can be detected statistically, like a ruler resting inside the cosmic web. The ruler is not one object, and it is not visible in a single galaxy. It emerges from the positions of many objects together. By comparing the apparent size of that ancient ruler at different redshifts, scientists can mark distances across different eras and trace cosmic expansion. That is why BAO is useful for dark energy. DESI does not look for dark energy as a glowing substance. It tests dark energy through its effect on the scale, timing, and spacing of cosmic structure. If the expansion history matches the simplest Lambda CDM prediction, then the constant dark energy picture remains strong. If the best data lean away from that prediction, the assumption begins to feel pressure. Not a dramatic break, but a measured tension between a clean model and a more complicated pattern. The first major DESI cosmology results, released in 2024, traced expansion history across roughly 11 billion years. That does not mean DESI measured the whole age of the cosmos. It means the survey reached deep enough into look-back time to compare much of the universe's later history. The results were broadly consistent with the standard model, while also showing hints that the story might be more complicated. Those results did not overthrow Lambda CDM, and they did not prove that dark energy changes. But when DESI data were combined with other cosmological evidence, some analyses suggested that dark energy might not behave exactly like a constant across time. Later results released in March 2025 strengthened that hint. With nearly 15 million galaxies and quasars gathered across 3 years of observations, the survey became larger and more detailed. The evidence still remained careful and conditional, but the pressure point became clearer. The old assumption under strain is the idea that dark energy is constant. If confirmed, that would force a revision of the standard cosmological model. That phrase matters because cosmology works by patience, not by a single dramatic announcement. Results must be checked against systematics, calibration choices, statistical methods, independent surveys, and alternative explanations. A hint can fade as more data arrive. It can also sharpen. For now, dark energy has not been solved, and the standard model is not dead. New maps have made the question harder to ignore. Dark energy helps determine cosmic fate. In the simplest picture, constant dark energy keeps driving accelerated expansion. Over enormous timescales, distant galaxies slip farther beyond reach. The universe grows colder and emptier on the largest scales, and local islands of gravity become more isolated. If dark energy changes over time, that ending may change too. Acceleration might weaken, strengthen, or require new physics to describe it. Some interpretations of the newest results suggest that dark energy may weaken over time. That possibility remains uncertain, but the finding matters. A weakening dark energy would not mean the universe stops changing, and it would not restore the old static cosmos. It would mean that the influence shaping the largest scale expansion is more dynamic than the simplest model assumed, making the future more conditional. This is why the newest map does not destroy the standard story. It refines the question at its center. The universe can still be measured. Galaxies still carry redshifts. Ancient pressure waves still leave a ruler in the cosmic web. The cosmic microwave background still anchors the early universe, and supernovae still trace distances across time. But the combined evidence may be pointing toward a model that needs more than a constant lambda. For a listener following the story from the old fixed sky, the change is almost circular. The universe looked still, then became vast, then began to expand, then accelerated, then seemed mathematically settled. Now the newest maps suggest the ending may still be unwritten. The lesson is not that science failed to finish the story. It is that better measurement changed what the story could honestly say. At the edge of certainty, dark energy remains a name for an effect whose nature is still unknown. It may be constant. It may evolve. It may point toward a new field, a changed equation, a deeper view of gravity, or a pattern that future data will clarify. The maps have not closed the question. They have carried it to the threshold where the story can finally rest. For now, the story can rest where it began, beneath a sky that once seemed fixed. That sky now carries motion, ancient light, acceleration, dark matter, dark energy, and new uncertainty. Each change came from a clearer way of measuring what was already there. The sky did not become less real because the story changed. It became deeper. That may be the quiet revelation at the end of this journey. The universe was never made smaller by being measured. It became stranger, wider, and more honest. Dark energy has a scientific name, a place in the equations, and a measurable effect on cosmic history. But its nature is still hidden. It may be constant. It may change. It may ask for new physics, or settle back into the simpler model when future evidence arrives. And maybe that is a quiet enough place to leave the universe tonight. Galaxies can keep moving beyond one another. Ancient light can keep crossing the dark. The cosmic web can keep holding its faint ruler across space. Somewhere beyond ordinary sight, the final direction remains unfinished. If you are still awake, more quiet lessons through history, science, invention, and the wider world will be waiting here. Or subscribe for notifications when new journeys begin. And if sleep has already found you, you're welcome to stay here, soundly, asleep in class.